So hello and welcome back to this machine learning course. In the last class, we discussed about classification and regression. In this video and the forthcoming videos, we will be discussing about regression in detail and today we will be picking up linear regression. We will be giving you a basic intuition of what exactly linear regression is all about. So let's get started. So in your 12th or 11th of your school, you must have done the Ohm's law experiment, wherein you will have to plot your V and I on the X or Y axis, and you would have to find the slope to this problem, because the slope would give you resistance and thus your Ohm's law would be verified. Now, for example, consider this statement over here, this graph over here. And for the time being, I assume that these are, okay, let me change the color. Are my Y's, V, and this is my I, okay? And I want to estimate my slope. So, for instance, if I join this line, these 2 points, if I join these 2 points, if I join these 2 points, and if I join these 2 points, is it actually a line? Of course not. It's not a line. No, do not judge it by me drawing curved lines, but actually if you see these points, the position of these points, you won't find them that they would actually form a straight line. They would actually form a crooked line. So you need to find a best fit line, which often your instructor or your teacher would actually tell you to find the best fit line. So that's what our objective is all about. So if instance you somehow draw this line, this is not your best fit line because this line does not appropriately represent all your data points most perfectly. So in this case, your best fit curve would be perhaps this line, and you could easily find the slope of this line, right? Or this line also. So since you need a slope, which is only a characteristics of a line, so you need a line. And so here in linear regression, we estimate all our characters or attributes to have a linear relation with the predicted output. So let's move on. So in the real world application, we often do not deal with single dimensional vectors, right? We deal with multi-dimensional vectors. And so single dimensional vectors are seldom easy to draw, easy to plot on the graph, but you cannot do so for multi-dimensional graphs because they would be taking you multi-dimensional analysis, and so which is very complicated, right? You need different hyperplanes in different modes, and so it is better not to get into that. So let's take a different approach towards this problem. What if you can represent your predicted output? Now let me show you what I mean by this. What if the Y, which is actually predicted by you, is represented in this format, right? Where x1, x2 up to xn represent the various features, and b1, b2 up to bn are actually constants. So let me show you an example. Now consider the table that I've shown you on this side, and this table is actually borrowed from a subset of Boston housing prices, which is actually a very large data set, but I've taken a small chunk of that. So this table or this column over here predicts in dollars about the price of certain degrees of house or something related to house, not into that much, and these are the various features which actually predict, which actually used for this predicting this value b. So this age is one factor, the age of the house, perhaps the tax on that house, the discount perhaps on the house, and so there are these terms of which people would maybe familiar about. And so these features are perhaps x1, x2 up to xn, right? These are the features till x1 to xn, as you can see in this equation here. and this y is assumed, this is assumed to be a linear combination of this vector, where b1 b where you the where the goal, your goal and your objective is to find out the best b vector which nearly predicts your output, right? Because this y which you are seeing over here is your predicted output, not your actual output, and your goal is to make this predicted output as close as possible to the actual outputs. Let me show you one more example. Now, as you can see over here, these dots, as you can see over here, are your actual outputs. But for example, if you want your predicted output to look something like this, is this the most best way that you can achieve this predicted output? Or let me consider this line as well. Is this the best possible way in which you can achieve your output? Or let me take it another example. Let's look at the actual one. Of course, I drew the correct line. So yeah, so is this the best possible output or the best prediction? Perhaps. And how are we actually doing this? So we need a mathematical method, because we cannot be dealing with graphs all the time, because your vectors are n-dimensional, they require complicated hyperplanes for dealing them, and they are way too complicated. We need a better way solution, and so we deal the problem mathematics. So why not? So let's take a look at this example. Consider this data point, okay, and this is my actual y. This is my actual y. I mean, this height is my actual y, and this height, as you can see, this is my actual y. This is my predicted y, denoted by y hat. Right? Now, I want my y hat to be as close as possible to y. I hope I'm correct. I hope it's all right till now. So, y, I want it as close as possible to this. So, I want this quantity to be as small as possible. I hope you are clear. Now, I want this not for a single point. I want this to have for all general points. I want it for this point, I want it for this point, I want it for this point, and I want it for this point as well. So there is either way, what you do is that you take up a line, you test for each and every point, or what you do, you add all these errors, right? For example, if I donate this as point 1, 2, 3, 4, 5. So these points, y1 minus y1 hat, y2 minus y2 hat, and so on. If I add all these errors, which I'm actually making, because these are nothing but errors, right? If, for example, I predicted this, so this is my error, right? This is my error. Now, if I add all this error, and for example, let me call this error as sigma, and I enforce a condition in my line, because my y1 is nothing but equal to m and mx plus c, and somehow I find an m and c which actually minimizes this sigma, my objective is reached. And so this green line which you are actually seeing, it is actually minimizing this sigma. So now the problem arises that, okay, this one is actually a negative error, this error is actually a positive error. So when you actually add this error, this could actually lead to a zero error, right? So even though you are actually committing a mistake, mathematically you are not committing any mistake, because your error is turned to be zero. So what we could do is that we could add a modulus out of here, right? You could add a modulus out of here, but Now you see, because all these must be positive, right? All of these equations must be positive. Now there's a problem with the modulus. The problem is that modulus turns any function into non-differentiable, and when we will dealing with gradient descent in further applications, you actually do not want your loss function or this function to be actually non-differentiable, right? So to make it positive as well as differentiable, we think we square this. We actually square this error, square this, right? Now it is perfectly differentiable as well as positive as well. So that is what we term as mean square error. I hope you now get the intuition behind the mean square error. If not, please write in the comment section. We will be there to dealing your problems. So yeah, so now this is the mean square error, and our objective and goal is to find m or c in two-dimensional case, or perhaps a b n-dimensional vector of b's such that b1 to bn, such that my vectors or my errors or the sigma value is this sigma mean square error is minimized, which is actually my goal or objective is all about. So that's it. So thank you for watching.
We'll be right back.